Right, hi everyone. Thanks all for braving the cold and coming here this evening. What I'm going to do first of all is rattle through a few of the sort of normal safety announcements, and then we'll get into the main talk of the evening. So first of all, welcome to Brandwatch. So in terms of fire safety, please, in the event of a fire, exit through the same route you came in, which is straight down the stairs and out the front door. If that route is blocked, please let a Brandwatch member of staff escort you to an alternative exit. Could Brandwatchers please make themselves known? I think it's basically just Luke in the corner and Phil. And please don't let any belongings obstruct the exit, though I don't think that's going to be a problem today. Not too many people here. So in terms of security, if you've not signed in, please do so. And please be aware the building is now locked, so if you do want to leave the building, you'll need someone, member of staff to let you back in. Also, please be aware that if the reception area door is open for 2 minutes, the alarm will go off, so please don't let that happen. And please don't wander that way into the Brandwatch offices because we're not supposed to go there because we don't work for Brandwatch. So for those who don't know, the toilets are down this corridor, down that way. And obviously you guys have found the pizza already. Tonight, the refreshments were sponsored by Crunch, and I'm just going to hand over to Jamie from Crunch for a couple of minutes. I think it's going to give us a bit of a chat. So over to you.
Yeah. Can you hear me? Okay. So yeah, it's literally will be a minute. I'm Jamie, and I'm in the engineering team at Crunch. I thought we'd take the opportunity to introduce ourselves as the sponsor of tonight. We're probably best known for online accountancy software, but recently we've also branched into mortgages and insurance too. So we're really trying to diversify. There's about 200 of us. We're based in Preston Park, 35 in the engineering team, and I'm sure like many of you, we're currently trying to break down a monolith into microservices with a React front end. It's pretty standard. But in the last few years, we've also gone on a bit of a journey towards continuous deployment too. And we've had some real highs and some real lows. But I think we're just about winning now. We've gone from doing about 1 deployment every month to 400. So yeah, that's probably more in October than we've done in the history of the company put together to date, 10 years. So it's really exciting, if terrifying. We hope to do a talk here next year, hopefully around Jan-Feb time, to go through some of the gotchas, potholes that we've stumbled into, but also talk about some of the successes we've had. Until that point, yeah, come and have a chat, or we've put our link to our tech blog here. Look, we try and keep it pretty updated. If you go onto Medium, just search Crunch, you should find us. Yeah, that's it from me, really. Hope you enjoy the chat, and yeah, hope to speak to you all soon.
Cool, thank you, Jamie. Sorry, Phil.
I've been told to set up.
Okay, fair enough. So just a quick announcement about the next Brighton Java. So that'll be in December at some time, I think about the 10th, we will announce it soon. It's going to be like a quiz night, so it's going to be some fun. It's like a pub quiz bit for programmers. There will be a prize involved. I'm not sure what it is yet, but it will be quite interesting, so please do come along. We're also looking for people at that event to do like lightning talks, maybe like 5-10 minutes. So if you've got an idea of like a talk, but maybe not like a full hour, and want to do a talk here, then please just let one of us know, and we'll get it set up. That'll be really awesome. Cool. So I'm going to hand over to Phil now for the main talk of the evening. Phil is a principal engineer at Brandwatch, and he's going to talk us through a database that he designed and built from scratch. So Phil, over to you.
Thank you. That sounds mad, doesn't it? Built a database from scratch. Relatively niche crowd tonight, so if you want to ask any questions during this talk, just stick your hand up and we can have a chat. I apologise in advance for my somewhat croaky voice. This is the 3rd time I've given a variant of this talk in public, and it's the 3rd time I've got the flu, so there's some sort of correlation there, if not causation. Yeah, so as Alex said, I am a principal engineer here at Brandwatch, and I'm going to talk to you about something called Memosyne, or Mnemosyne as you're actually supposed to pronounce it. So Mnemosyne is the Greek titan of memory. We've spent the last year calling it Memosyne, and last week I was talking to a Greek scholar, and she told me that that's not actually how you pronounce it. So you'll also hear me switch between both pronunciations as and when I remember. So I kind of apologise for that, but not really. So this talk, yep, that's working, cool. So this talk, going to split it into sort of 4 sections. The first one, I'm going to spend maybe 5 minutes just talking about the problem we were trying to solve and why we ended up building a database ourselves, because that's one of the things that's like a huge no-no in general. So I thought I'd give a little bit of an explanation, not just that we decided to have some fun. I'm then going to kind of look at the sort of very high-level architecture, so you sort of understand how the bits fit together. And then there are going to be a couple of deep dives. I'm going to look at how we store stuff, and then find it using indexes and queries, and how that all sort of works from a kind of bottom-up kind of approach. And then the second half of that is, like, now you found some data, how do you do stuff with it? And in our case, that's how do you do aggregations at scale using GPUs, CUDA, and those sort of things. And again, any questions, stick your hands up, and I'm happy to answer as we go along. Or you can wait until the end. Entirely up to you. So, oops, is that working? Yeah, okay, cool. Right, so part one, the product. I'll keep this brief because you're not really the end users for this product. We're a marketing company. We build tools for marketers. There's probably no marketers in here. Brandwatch Audiences is a product that allows people to understand groups of people online. So our customers will find, groups of people on Twitter, and then try and understand what makes them tick, what makes them distinctive from the background, how they're interesting, what they're up to, how the conversation is changing over time, all those sort of things. And the UI and sort of process is quite simple. So this is like the home page of the app. You can build audiences using query parameters. There's a whole range of different operators. There's free text search. There's the ability to find people based on who they're following on Twitter, a whole range of sort of things. And then once you've constructed an audience, we give some sort of high-level details. So this is the DevOps and Brighton Java crowd. Not many people follow Brighton Java on Twitter for some reason. So I've created an audience here that's Brighton Java, following either DevOps or the Brighton Java account, and have mentioned the word Java. None of the demographics there are particularly surprising. So we have the top profession is, surprise, surprise, software development and IT. Unfortunately, the gender breakdown is heavily biased towards blokes, which is unfortunate the way it is in the industry at the moment. And you can see some of the keywords in bios, all the sort of stuff you'd expect. We then move through and you can see what sort of content people are sharing. Again, for this audience, it's all pretty straightforward. It's stuff about Java and about conferences and those sort of things. Nothing so exciting really in this case. And then we can see who's influential. I was actually a little surprised that Oracle's Code 1 was the most influential account in this audience. Maybe it's because I just don't like Oracle, I don't know, but there you go. And we show you, who's influential from the audience and who's influential from outside. And this is done by looking at all of the content that people have shared and all of the app mentions that people have sent on Twitter. So if you app mention somebody in this audience many times and they respond, then you'll be counted as influential. So this is done over tweet data. And then the final piece of the puzzle is conversations. So we break down what people are saying. So we show you what sort of themes they're interested in, what sort of subjects, and how this is indexed against the global background. So you can construct an audience of any size, and then we'll compare it to the whole of Twitter. And then finally, if you see something that's interesting, you can kind of click through. So we show hashtags, and this is a gaming hashtag. I'm not really a gamer, but PS4 share sounds like that. And we show the content that's being shared using that hashtag and the activity on that particular entity over time. And again, this is done against all of the content shared by a given audience. So that's the kind of the problem space and the sort of product that we're building. But there are some things that make this quite interesting. So the first is the scale. So we have access to the Twitter firehose. We ingest the Twitter firehose. At the moment in the system itself, we have about 100 billion entities. And you can construct an audience that will touch most of those. So I can construct an audience that is all of the individuals on Twitter, which is about 500 million people. And then we'll go and look at all of the content they've sent in the last 3 to 6 months, which is quite a lot of stuff. And then we'll again look at the entities that are mentioned in that content. So if you use a hashtag or if you use an app mention, we'll go and look at that. So the scale is quite large and sort of unusually so. That's the total number of entities. We see quite a lot of updates as well. So we see about 100,000 updates a second on average coming into the system. Not completely excessive numbers, but again, not a trivial amount. So if you send a tweet, we'll ingest that tweet. We'll send it through our machine learning pipeline, pull out a bunch of entities, do some inference, and in total this adds up to about 100,000 updates a second. So again, the scale is quite large, and there's quite a lot of churn, quite a lot of updates. And then the final piece of the puzzle that was a real problem, of course, is the types of queries we allow people to construct. So we support free text queries. So you can construct an audience based on everybody who has used a particular term or phrase on the whole of Twitter in the last 3 months. So that obviously means doing a free text index across tens of billions of tweets. Ironically, that wasn't the hardest part of this problem. The hardest part was actually categorical data, right? So categorical data is kind of attribute-based stuff, like if you are an individual or an organization. So categorical kind of attributes can be very selective. So find me people that live in Brighton, and that's maybe a category, and that might be a few thousand people. Or find me people who are men, and that's suddenly 500 million people. So categorical queries are actually quite tricky because they can be very, very selective or very unselective. And then finally, we support graph queries. So find me all the people who are following the Donald Trump account, and there's like 50 million of those people. Or find people that are following me, and there's 200 of those people. So again, the scale sort of varies up and down. And the final part is that this all happens in real time. So this is a real-time product. So people can go in, construct a query, get results back in a second, less than a second ideally. All the time while data is changing, new tweets are coming in, new entities are being mentioned, and people expect to see that being reflected in the data. So we've got lots of churn, high scale, difficult queries. We kind of looked at a bunch of off-the-shelf solutions. Our original platform was built on Elasticsearch. We way exceeded the capabilities of that. We looked around at a whole pile of other open source solutions and commercial solutions, including things like MemSQL, but nothing really ticked all of those boxes. So we ended up building our own thing. If you care a bit more about the background of why we made that decision, I did a talk at DevOps where I can drill into that a bit more. Obviously, time here is a bit more limited, and the technical stuff is far more interesting. So let's talk about Memosyne, or Mnemosyne, as I should call it. So Mnemosyne is a shared nothing distributed indexing and query layer. And by that, I mean it doesn't necessarily store all of the data that we use. It only stores the data required to answer queries, things that require to go into indexes or things that are required for aggregations. And I'll explain a bit more about how that works in a sec. So for a very sort of high level, this is kind of what the architecture looks like. And I'm going to try and use my little pointy thing here, which might work or might not. Obviously, anybody on YouTube won't see this, but never mind. Yeah, okay, cool. So Memosyne nodes kind of act in isolation on shards of data. And we have a Google RPC API, which is a nice protobuf-based sort of RPC mechanism. It's a really nice library if you've not come across that. And then inside, we have a bunch of the usual sort of databasey things. So we have a query planner that takes a query and works out how best to execute it, how to optimize it. We have a framework that does aggregations, things like top N, histogram, unique counts, those sort of things. We have a big whacking CUDA acceleration library to make things go really fast on GPUs, and I'll cover that in the last deep dive. And then we have a variety of indexes that support different types of queries, like free text indexes, log-structured merge trees for point queries, those sort of things. And then we use Kafka to connect all of these things together. So we have multiple instances of this running, and these subscribe to particular topics on Kafka and index bits of data. And Kafka is basically our record of truth. So we can kill all of these instances, all of these Memosyne nodes, and then recover data from Kafka, which allowed us to move really, really quickly. At the top here, we have a query proxy that basically takes a query, works out how to distribute bits of it to different nodes, and then stitches the result set back together later on. Architecturally, there are multiple Memosyne nodes. There's a query proxy that talks to them all. Client applications talk to the query proxy, not to Memosyne nodes, and there can be multiple instances of this thing running. And then the full data set is stored in a key value store, which I'll talk about in a little bit. So again, this is just about indexing and querying things, not about kind of materializing or deserializing full records. So if you're building a database, the first place to start is how you store stuff, and then find it again. That's kind of the key point of the whole system. So I talked about only storing data that's required for answering queries. And the main reason for this is that in our use case, we have quite relaxed constraints around consistency. So if we lose a tweet, a single tweet, it's no big deal. People aren't going to notice there are 10 billion tweets a month or a week or whatever it is. You lose one, it's not going to matter. Obviously, if you're building a financial app, then it does matter. You want to have strong consistency and strong availability and those sort of things. So we took quite a relaxed approach to this. We take, for example, a Twitter profile like this, and some of that stuff goes into an index, like the text for free text searches. Some of that stuff might go into stored fields for use for aggregations. And then the rest of it, which is only really useful for display, like, I'm not going to query on the avatar URL, that goes into a third-party key value store. And we use Cassandra for that, running across a cluster. We have previously used Mongo, but Cassandra ended up winning the battle there. So I guess the next question is, right, we want to store some data, not all of the data. Where do we store it? So the obvious thing is on, fast storage like SSDs. So these are NVMe PCI Express SSDs. You can get about 4 gigabytes a second of data going in and out of these things, so pretty fast. And they're quite cheap as well. So a terabyte of enterprise NVMe drives is about £500–600. So you can have fairly large amounts of data on pretty fast storage. But there's obviously one thing that's even faster than PCI Express SSDs, and that is RAM. So we have invested heavily in storing and compressing stuff to keep it in memory. Because if you can get stuff in memory, you're talking about 120 gigabytes a second of bandwidth compared to sort of 4 gigabytes a second per drive. So the more data you can get into memory, the better. So we run this application on boxes that have got 512 gigs of RAM spread out across a large cluster. The price point isn't as bad as you might think. So a terabyte of DDR4 RAM is about £10,000. So quite a lot more than SSDs, but probably not as much as you might imagine. But there is a problem. So this is all written in Java, and that problem is related to this thing. So this is the sexiest picture of a garbage truck I could possibly find. Yeah, so when you're writing a Java application, the obvious choice is to put things on heap. So you just do a new object, new foo, and then I'll keep it on heap. It's really easy to use. We're all used to doing it. There's no manual memory allocation. It's very safe. There's no range checking. You can't trample on memory. You can't cause seg faults and all that sort of thing. But there is a downside, and the downside is it's not actually very efficient. So if we look at, for example, a string, 8 chars, exclamation mark, the UTF-16 data for that is about 16 bytes. So that's not very much. But in Java, 64-bit JVM, that uses up to 64 bytes of memory. So there's the 16 bytes of JVM overhead, which you get for every single object. You have some bookkeeping data inside the string itself, which in hotspot Java 10 is about 12 bytes. You have a pointer from the Java string object to an underlying string array. And on a 64-bit JVM, that's often 8 bytes. And then you have char, which in Java is like an object. And again, you have that 16 bytes of JVM overhead, and then you have the actual data. So you've gone from 16 bytes of pretty simple text to 68 bytes of data in the heap. And that's exacerbated by what happens when you throw hotspot at a very large heap, 256, 512 gigs, a terabyte. And that's basically this happens. So it gets pretty angry. You can buy JVMs that are designed to work with very large heaps. So Azul makes something called Zing, which is designed for that, real-time applications on very, very large heaps. But it's really expensive, like really expensive. So we ended up doing what most people do, which is to use off-heap memory. So this is kind of like using heap memory for like short-lived objects, and then using a great big whacking slab of off-heap memory for most of the actual data. Obviously, there are downsides in that this is not very safe, and you can get yourself into trouble, and things break, and it's just like working in C. But it does mean you can eke out, lots of efficiency from that. And then we obviously map everything to memory map files underneath as well. So that's kind of storing data. Nothing particularly revolutionary there, I don't think. How do we find stuff? How do we query things? So slight diversion here into something called the algebra of sets, which is quite a fancy term for basically something that describes how you can describe the interactions between groups of things. So a set is just a collection of things, and the algebra of sets describes how those things can be combined in various predictable kind of ways. And what's that got to do with databases? Well, imagine a profile, a very simple profile. So we have 3 attributes. We've got a profession. Maybe that's a multi-valued attribute because people can have more than one job. Maybe you've got a location. Maybe that's a single attribute because people only live in one place, typically. And then maybe you've got something that describes the other profiles they're following, and there might be multiple ones of those. So you can take this fairly basic entity, and you can represent these as sets. So for example, we could have a set which is Twitter users in the UK, and we can have a set which is Twitter users who are politicians, and we can have a set which is Twitter users who follow Google, and so on and so forth across all of the attributes in the entire space in this application. And then we can use those sets, and we can use the algebra of sets to interact with them. So for example, to find Twitter users in the UK who are politicians, we could find the intersection between those two sets. And if we wanted to find Twitter users in the UK who are politicians and who also follow Google, we could find the intersection between all 3 of those sets. I didn't draw that because it's actually quite hard to draw a 3-way intersection in Google presentations, as I discovered. So you can take this model and you can use it to describe basically any sort of relational style algebra, which is pretty cool. More generally, you can say we have a collection of records over here, records, and we have something called a predicate here, which basically describes how to take records and put those records into a set. So this predicate X puts things into this set here. And that's quite a powerful way of thinking about it, because a predicate could be an index. You could have a free text index, or it could be a brute force scan across a region of memory, or anything in between. So it's quite a nice, natural, generic way of kind of describing those things. So how do we then use those sets and actually sort of materialize that in Java? So the sort of, I guess, obvious approach would be to take the smallest set. So let's say politicians is the smallest set here, and then basically go over every single politician in the politician set, and then check to see whether they exist in the other sets we're interested in, and then that will give us the intersection, and we can do something with that. And as Java developers, we're kind of used to sets being like really fast, like they're like the fastest data structure in Java, right? Fantastic. And they sort of are, but there is quite a lot of overhead involved. So if you want to do an intersection, you're going to calculate the hash code of this thing. Normally in Java, these sets are underpinned by an array, so you're going to calculate an array offset, you're going to do a lookup in that array, that's probably going to cause a cache miss because it's going to be somewhere in sort of random memory. And it becomes quite expensive. So doing an intersection on this laptop with a couple of 100 million things in a set takes a few seconds, which is pretty speedy, but not as fast as we'd like it to be, because we're talking about doing that on potentially billions of things. Now, there is a solution to this, otherwise this story would have been very short. And the solution is actually arguably the simplest data structure you can come across, which is the bit set, or bit array, or bitmap. All that basically is a sequence of bytes, and you say, this bit in this byte maps to some entity, entity 1, let's say, and if entity 1 has an attribute, we set it to 1, so more obviously. So say we have the users who are politicians set. We say user 1 is a politician, so we set bit 1 to true, because he's a politician. User 8 is not, so we set bit 8 to false. And we can extend that so we can add as many bytes as we want. So say there are 16 people in our set, we can have 16 bits, 8 bytes. And then we can start to combine them. And this is where it starts to get quite interesting, because we can use very fast CPU instructions to do those combinations. So we can do bitwise ANDs, and that'll give us the union of those sets. We can do bitwise ORs, and that'll give us the intersection of those sets, which is kind of cool. And the reason why it works very well is because modern CPUs have instructions that will do multiple bytes simultaneously. So you can do a bitwise operation on multiple bytes simultaneously. So AVX512 will allow you to do that on 512 bits. So you're doing a hash set style operation on 512 bits in a single CPU cycle. So it allows you to do this set algebra at incredible scale and incredible speed, which is really pretty cool. And then we can take this a little bit further, and we can use this model to represent queries as well. So we have here a real query taken from the system. So we have, it's a kind of politics query. There's a bit of a theme here, so sorry about that. So we look for people that are following either Trump, Obama, or Clinton, and we look for ones that don't have the Russian bots tag set, but have tweeted the word politics and have a score, an influence score over 80. And these can all be represented as bitmap operations, which again is a nice natural way of representing it. So in the real world, this might be a raw row scan. So we just scan across the profiles and look for profiles that have a score of greater than 80. This could be a Lucene index. We use Lucene for free text indexes. So we look for people that tweeted politics. This could be just a bitmap, because it's a Boolean condition, if it's a bot or not. And the same down here. So by applying all these techniques, we can execute queries at speed. We can combine together all these different types of indexes where, you know, the output from a Lucene index doesn't necessarily look like the output from a log-structured merge tree or whatever. And do it at speed and in a way that sort of makes sense from kind of a Boolean algebra perspective. But of course, there's always a downside. And before I tell you what the downside is, I'm going to take a drink. Okay. So the downside is memory. Anybody in here recognises that? Probably not. No? Okay. You do. Cool. So this is core memory. And each of these is a bit, basically, which obviously maps to our bitmap. And bitmaps can actually get quite expensive because, you know, you think about we have, say, 480 million Twitter profiles. 480 million bits is 60 megabytes. And then you replicate that for every single attribute that you're indexing. Suddenly you're using up lots and lots of memory. Even though it can go really, really fast, it becomes very expensive. A better representation of that is this. So this is these are 3 different bitmaps for different attributes. This bitmap on your left here is close to optimal, okay? So it's pretty random data. It's hard to see any pattern. It's hard, therefore, to compress it. This bitmap is pretty terrible. It's very, very sparse. There's not much going on. There are whole blocks of empty bits. Okay, so you can think of immediately lots of naive ways that you could then compress that to make it a smaller representation. And this is sort of the inverse of that, where it's very, very high occupancy, a relatively few number of unset bits. And again, it's not as efficient as you could imagine. Okay, so thankfully there is a solution to this particular problem, and that's something called roaring bitmaps. So roaring bitmaps is sort of like the latest in a whole line of ways of compressing bitmaps, and it's quite notable because it does it in a way that gets rid of lots of downsides. So like an obvious way of compressing a bitmap might be to use run length encoding, where you'll find sequences of bits, and you'll say, oh, this sequence is all set to 1 or all set to 0, so I'll compress it using run length encoding. That makes it quite hard to do random access, which kind of negates the whole point of using bitmaps in the first place. So what the people behind roaring have done is realize that in real-world applications, different bits of a bitmap can be compressed in different ways. Okay, so They split it into chunks of 2 to the 16 integers, and each chunk can be stored in one of 3 different ways depending on the type of data inside of it. So best case is it's stored as an uncompressed bitmap. Okay, there's no smaller way of compressing it, no smaller way of representing it, and that's great because that just works like a normal bitmap, nice and fast. The next way is to store just a list of numbers. So if you have a bitmap that has very low occupancy, like this one, we've only got the first bit and the 63rd bit set, we can just store that as two bytes, okay, which gives us a pretty significant compression overhead. Obviously, then doing bit set operations on those is more expensive because you're falling back to doing sort of more sort of high-level instructions, but the memory saving can often be worth it. And then the third way is to store ranges, which sort of works in the same way. So here we have, again, 2 ranges that are set, and we can store these as 4 bytes in total. Again, 2 bytes and 2 bytes, sort of start and end. So that's kind of cool. Allows us to have bitmaps that in most cases work as fast as a normal uncompressed bitmap, but also allows us to save a lot of space in cases where we have lots of sparsity. The final piece then is obviously making sure that we map bitmaps to underlying data. Okay, and this is kind of key. So imagine we have these professions attached to a profile. So we have executives, we have artists, we have scientists, and we have sports people. We want to make sure that profile 1 is always mapped to the same offset in the bit sets, so we can combine them without having to do any sort of transformations or lookups. So in Memosyne, we take records in, we assign each unique entity ID an ID, a monotonically increasing integer, and then that basically refers to the offset in all the underlying bitmaps. So that's pretty cool. The last, the last part of the puzzle is doing stuff with that data. Okay, so we've got some records back, maybe many billions of records. How can we do aggregations and provide insights on that data? And the solution that we ended up coming up with is to use these things. Not these specific ones because they're very expensive, but so this is an NVIDIA Tesla card. These are great for embarrassingly parallel problems. So if you can take your problem and you can break it down into lots of little segments that can operate mostly independently, GPU is a great way of doing it. So you might look at like a diagram like this, which is a sort of the block diagram of a NVIDIA 1080 card, and think, wow, look at all these tiny little processors. It's going to be really easy to build code for this. Unfortunately, it's not, and despite being very deceptively easy to think about it as a sort of massively parallel processor, things get a bit more complicated. So each NVIDIA GPU has multiple streaming multiprocessors, and this is kind of, I guess, analogous to a socketed CPU, right? So you can imagine in this case there are 1, 2, 3, 4, 5. So there's like 5 of these socketed CPUs in this block, and another 5, and another 5, and another 5. And then when we zoom into those, we see that there are multiple little CUDA cores, and these CUDA cores are kind of similar to a CPU, a very, very simplified cut-down CPU with lots of restrictions. The main restriction is the way the data model works. So we've probably all heard of SIMD, which is single instruction, multiple data, SSE, MMX, those sort of things. So you can take a single instruction and say, I'd like to do this operation on 4 bits of data simultaneously. CUDA cards use something called SIMD, which is single instruction, multiple thread, which is sort of in between your generic general purpose CPU and your very specific SIMD processors. And the basic idea here is that you write your code, you have threads, and these threads operate in lockstep across random distributed data. So the data is itself whatever random data you've got, but the threads are kind of operating in lockstep, which seems a bit crazy. It seems really, really limiting. I mean, how do you write kind of code that works performantly there? And the answer there is actually in the way the memory models work. So on the left-hand side here, on the right-hand side, your left to my right, we have a Xeon Platinum CPU. This thing has multiple cores, and each core has 1.3 megabytes of level 3 cache, has 1 megabyte of level 2 cache, and has 64 kilobytes of level 1 cache. And the bandwidth between these two things is 480 gigabytes a second. It's pretty quick. The bandwidth between main memory and this part is just 120 gigabytes a second. And this is shared across all of the cores on the die. So if you've got a 64-core processor, that 120 gigabytes a second is split into 64 bits, or 64 shared components. This over here is a GPU, and we have a similar-looking sort of structure. We have 11 megabytes of main memory. We have 2 megabytes of level 2 cache, and then each CUDA core has access to 48 kilobytes of level 1 and 96 kilobytes of something called shared memory, but they're sort of the same. But the bandwidth here is a lot higher. So the bandwidth from like main memory is 480 gigabytes a second, and the bandwidth from your level 2 cache is 2 terabytes a second, which is like, incredibly speedy. Unfortunately, the connection from main memory to your GPU is just 16 gigabytes a second. So you need to be quite careful about moving data across. So actually, moving data from main memory to the GPU is the most expensive operation you normally perform. Actually, acting on that data is often much quicker than that particular operation. And to sort of demonstrate that, this is a very simple example of a kind of a CUDA app, where we basically want to count the number of unique things in this data set. And if you were going to implement that in Java, maybe you would start with a hash set. So you would start with, hash map, and the key is the value, and the value is the count. And we'd start with, right, number 5. Okay, I'm going to put that on the hash map and add 1 to the value, number 6, and so on and so forth. Because of the way you can access memory on GPUs, the more efficient way of doing that is actually to first sort the data. And there are very high-performance parallel sorting algorithms like radix sort that allow you to do that at scale. And then once you've sorted it, you again in parallel scan across it and basically find the boundaries between each of these blocks. And then that gives you the final count. So it's quite a different way of thinking about building these algorithms, quite different from the sort of procedural style code that you'd write in a normal CPU. So this allows you to build things like aggregations at great scale that run very, very fast. So for example, you can sort 1 billion integers a second on a 1080 card, which is about an order of magnitude faster than on a 64-core Xeon processor, which is quite impressive in its own right. Unfortunately, there's always a downside. In this case, the downside is, you can actually see that. To write CUDA code, you're almost certainly going to end up writing C++ code. Ooh. You can see it better now. I don't think it's any better when you can see it, but there you go. And the interface between Java and C++ is pretty messy and pretty nasty. So this is an example of some code that basically built a histogram, so puts things into bins and then counts the bins. And there are some nice libraries in C++ land, like Thrust, that basically provide primitives for doing these sort of things that work quite well. But then the interface with Java becomes quite painful. So what we ended up doing was basically building our templated CUDA code and then slapping a C API layer on top, and then using something called JNA, which is Java Native Access, which is kind of like JNI, but without all of the boilerplate. So you basically write an interface in Java, and the interface kind of conforms to the interface you'd find in your C code, and then JNA basically maps it to that native code. So you don't have to write lots of C++ headers and use the JNI compiler and all that sort of stuff. And that allows us to basically to do high-speed stuff in CUDA land on the GPU. Any questions? Many, hopefully.
So I was interested in the entity IDs you're using to index into the bitmaps.
Yeah.
Presumably that is absolutely critical data, because if you lose that, all the bitmaps become garbage.
Yeah, exactly. Just random data. You could use it as a source of entropy. Yeah, absolutely. So the most critical part is when the data comes in and we assign it an ID, that ID is then flushed to disk, to a log, so that we don't lose it. But yeah, if you lost track of that, then obviously things wouldn't line up, and you'd do a query, and the result set that came back would be just nonsense. So yeah, that's very important.
How often would you have to do a stock take of the indices against the data that's supposed to be indexed? Presumably they can somehow get out.
No. So we don't do stock taking. So we have a whole range of integration and sort of stress tests that basically kind of pre-validate that the code is functionally correct. I guess in theory you could scan across the data again later on and check that it all matches, but it's not something we've necessarily found the need to do. Yeah, but yeah, I guess in some ways we seem a bit sort of blasé and relaxed about this because we're dealing with social media data, and like losing the odd thing kind of doesn't matter, and we can always re-ingest. We built it so that we can rapidly re-index things if necessary.
Presumably you have to get a special compiler, C++ compiler for the graphics processors. That was, I suspect, quite a selection exercise using the graphics processors.
Sort of, yeah. So this is actually a question that's come up before, and I gave it some thought, which is quite interesting. So AMD cards, if you actually look at the architecture and the like the underpinnings from a kind of silicon perspective, are actually quite interesting and in some ways more general purpose than NVIDIA cards. But AMD's toolchain is terrible. And as a developer, I'm actually quite happy to throw a bit more money at hardware, like buy 8 cards instead of 6, and have a much easier life with the toolchain. And NVIDIA's toolchain is actually pretty good. So they've got an Eclipse-based IDE that's got like profiling applications, so you can profile your CUDA code, and it ships with a C++ compiler. It's very tempting to sort of view all the CUDA code as like normal C++, but it's kind of a sort of a slightly specialized selection. So you know, it can get a bit complicated, but actually the documentation is very good as well. So that was the main reason for choosing NVIDIA rather than AMD. So there's 2 types of testing we do. So we have random tests where we just generate random data every time we run it, and then basically validate the data using just brute force. So we'll ingest the data, run some queries, and then run the same queries just brute force across the underlying data and check that things all sort of line up, which is a good way of catching just like edge cases and things. One of the guys in the team is having lots of fun at the moment because he's written a new aggregation and there's an edge case that he can't quite track down that keeps crashing things. But these tests are catching it, which is kind of cool. And then there's the, here's a fixed data set that we know has certain properties, and then we can look at those properties. And then there's the high-level operational monitoring where we'll actually look at, like the numbers of certain types of entities. And unless something dramatic happened in Twitter land, you wouldn't expect to see deviations from, say, the last 5 days. Mm. That's a good question. So part of the wider story is when we built this system, we moved it off Amazon. So we were hosted in Amazon before, and we were using Elasticsearch. Brandwatch has a big investment in data centers and people to run data centers and that sort of thing. So for this product, it sort of made sense to buy some hardware. And we spent about £250,000 on hardware, which was less than a year's worth of Amazon bill. And that hardware will last 3 to 4 years, depending on how it gets deprecated. Which seems like a lot of money, but the product makes lots of money as well, so it's sort of kind of a good trade-off. So when you're in a sort of physical data center, you're not necessarily exposed to some of the problems you get on the public cloud. Like, you could be on an EC2 instance and the other person on the instance is doing something crazy, and it's just, so you're right. So I guess it's kind of a cheating answer, is that we actually moved it onto physical hardware where there's more predictability. Yeah. Good question. Yeah, exactly. So it's in some ways it's like any database design decision. You decide what your schema looks like. So there's a schema format that's just YAML that says, these are the fields and these are the types of indexes I'd like to build. So it's in some ways it's a little more. Yes and no. So like an index might be like, I would like to have a free text indexed on the tweet content field, and then that in turn, it's a free text index. It can answer any sort of free text kind of query. So as long as you have the right types of index on a field, you can answer, in a generic sort of way, most types of queries that would access that field.